So this is example number, I believe, 4. There we go, 4 in your unit handout. And I'm telling you that sometimes you need to differentiate things multiple or integrate things with parts multiple times in order for it to work. So what we've got here is the integral of x squared e to the 2x dx, and you want to find what that's equal to. So you would say to yourself, I'm going to do parts, not just because it's in the lesson on integration by parts, but because it looks like it's parts. You'll start to recognize all of these as being like usually a polynomial term like x squared and a trigonometric term like sine of 2x, or a polynomial term and an exponential term, or a polynomial term and a logarithmic term. Doesn't have to be those three situations. It could branch out from there. But we're going to choose x squared as being, u, which makes 2x dx du. And for dv, since we chose x squared, we have to choose e to the 2x dx, the rest of the integrand, and the antiderivative of that is 1/2 e to the 2x. And again, that's something that I think you should just be very familiar with right now. That if you anti-differentiate e to the, you're going to get e to the with what I call a corrective measure out in front. In this case, we need 1/2 because of the chain rule, which is going to produce a 2 in differentiating this. So now we can write out what this is equal to. This is the integral of x squared e to the 2x dx is equal to the product of these We're okay with that? Minus the integral of the product of these And I don't think even if this were a written response question, I would expect you to write 1/2 e to the x times 2x dx and then change it to 1. The 1/2 times the 2 is pretty obvious that it goes away. But the problem is now when you look at this integral, it requires integration by parts to figure out. What we need to do now is choose, and I'm talking about for this integrand, we're choosing x for u, which means du in this integrand is dx. We're choosing e to the 2x dx for dv, which means v is 1/2 e to the 2x. And the thing that you have to be careful of here is this integral here, everybody. This integral is going to be a uv minus the integral of v du, but we're subtracting that integral. Right? It says up here that our answer is going to be 1/2 x squared e to the 2x minus this integral. And this integral contains multiple terms. So you need a set of brackets, in other words. So from the top of the screen, this is where we're at. The integral of x squared e to the 2x dx equals 1/2 x squared e to the 2x minus this integral, which is uv. This whole integral is that thing that I've got highlighted here in the middle of the screen. uv will be the product of these, which is 1/2 x e to the 2x minus the integral of the product of those, which is 1/2 e to the 2x dx. It's no different than when you subtract anything that has multiple terms. You put that thing in brackets. So we get the integral of x squared e to the 2x dx equals 1/2 x squared e to the 2x minus 1/2 x e to the 2x. I'm perfectly aware that many of you could combine this step and the final step in one fell swoop, and that's fine. Just be careful. I'm not going to. I'm going to say minus a negative is positive, the integral, and I'm going to factor that 1/2 out. how many of you might be inclined to have just said it's going to be plus 1/4 e to the 2x? You might have skipped that step, but not too many people, I don't think, because I think you're rolling the dice there. You could easily get an incorrect answer. We can finish this off now and write 1/2 x squared e to the 2x minus 1/2 x e to the 2x plus 1/2 times the integral of e to the 2x, which is 1/2 e to the 2x, plus our constant. So our final answer is 1/2 x squared e to the 2x minus 1/2 x e to the 2x plus 1/4 e to the 2x plus c. And I did take the time to write out that 1/2 times 1/2 is 1/4 because I want to show something to you. I want to show you that this in fact is correct. Don't forget, if we differentiate what I'm highlighting in yellow and we get what I'm highlighting in green, then what I've got in yellow is the correct answer. For the first and the second term, so I'm going to differentiate with respect to x, that yellow thing. The first and the second term, they're both products, so I have to use the product rule. The derivative of the first would be x times the second is e to the 2x, plus the first is 1/2 x squared, times the derivative of the second is 2 e to the 2x. I'll just let you percolate on that for a second. Does that look okay? I want you to notice that this is what we're after. We look up here at what we were trying to anti-differentiate. We're trying to anti-differentiate x squared e to the 2x, which is what that is. So hopefully everything else that follows is going to cancel somehow. Minus product rule, derivative of the first is 1/2 times the second plus the first, which is 1/2 x, times the derivative of the second, which is 2e to the 2x. A totally different note here. How many of you, in differentiating this, would have put the negative with the 1/2 x and thought of it as part of the first? Okay. You should be fine with me not doing it that way then. I'll just double check that. 1/2 is the derivative of the first times the second. 1/2 x is the first times the derivative of the second. This is nice because if you look at what we have here, this is x e to the 2x, and we're subtracting it, and out in front we have x e to the 2x. And I've got a pretty significant mathematical flaw in what I've written. This is equal to the derivative. Right? And then plus the derivative of this, which will be 1/4 e to the 2x times 2. So what do we get? I mean, how many of you see that we're getting the right result? Okay, I'll write it all out to be explicit. I have x e to the 2x. I have plus x squared e to the 2x. I have minus 1/2 e to the 2x. I have minus 1/2, minus x e to the 2x. And I have plus 1/2 e to the 2x. So these two are opposites, they add to 0. These two are opposites, they add to 0. The derivative of the constant, of course, is 0. So you get x squared e to the 2x. Look at one final example here today, and that is e to the x sine x dx. And I'm telling you right at the beginning, we're going to have to use integration by parts twice. I'm not telling you why yet. I want you to notice that no matter what we choose for u, it's not going to become simpler. It's not. If I choose e to the x as u, then du is e to the x. If I choose e to the x as dv, then v is e to the x. I don't even have that 2 or a half to worry about. And it's not really valuable to say that sine of x is going to become simpler when you differentiate it, because it just becomes cos of x. And nothing inherently simpler about cos of x compared to sine of x. I will tell you right now that it doesn't matter which one you choose, though, and parts will give us the solution. So because it's easier to anti-differentiate e to the x, I'm going to put e to the x dx there. I mean, is it like intellectually challenging to anti-differentiate sine of x? No. But it requires a little bit more thought. And that means I'm going to put sine of x here. And that means I get cos of x dx here. And that is telling me that the integral of e to the x sine x dx, this is the thing we're trying to find, is equal to, once again, I forgot to finish my thought here, the antiderivative of e to the x dx is e to the x. And if it were e to the 2x, then we'd have a half there, that's all. Is the product of these minus the integral of the product of these. And I think you would make the argument, probably making it in your head as we speak, that that doesn't really help us. It doesn't help us, because if you knew how to integrate e to the x cos x, I would assume you knew how to integrate e to the x sine x. There's no inherent difference between sines and cosines in terms of operations. They're different things. But they're not different like the natural logarithm of something and the number 5. Those are different things, really different. But let's do integration by parts again, and let's keep the same choice in our mind, namely that I'm going to keep choosing e to the x dx as dv, and the trigonometric component I'm going to choose to be u. So what do I get? I get du is negative sine x dx, and v is e to the x. Don't forget, I'm anti-differentiating this way. For goodness sake, never use that as a mathematical abbreviation in university. And we are differentiating this way. So what do we get? We get the integral of e to the x sine x is equal to e to the x sine x minus the product in brackets, minus in brackets, the product of uv, which is e to the x cos x, minus inside of the brackets the integral of negative e to the x sine x. Now we have a boatload of negatives here when you look at that, don't we? So the first thing to note, if you can handle this in one shot, that's great. Absolutely handle it in one shot. But I'm going to do this in a couple of steps. I have e to the x sine x minus, in brackets, e to the x cos x plus the integral of e to the x sine x. So the only thing, dx, the only thing, everybody, I've done here is I've said that I'm going to take this negative 1 in the integral, bless you, negative 1 in the integral right here, and I'm going to factor it out in front because that's a property of integrals, and the negative 1 outside multiplied by the negative 1 as a coefficient in front gives us positive 1. And then when I finally peel off the brackets, I have this statement. And, you know, you're back at the beginning. We're back saying, well, if I want to proceed, I'm going to have to use integration by parts here, and I think you see we would get an infinite series of terms that we're going to be adding together, and we never get to a satisfactory conclusion. But I am going to tell you that the answer to this problem is one, maybe two steps away. It's right there. And I'm going to give you a minute to see if you can crack it. It's got nothing to do with identities. If you do get it, put your hand up and down. I think those people who got it, and there's 2 or 3 of you, would agree what we've essentially done is found out what the integral of that is without ever anti-differentiating it. The key is, and I don't know if you noticed, but sometimes students get annoyed with me for this, I keep writing the integral of e to the x sine x dx equals. I keep writing this. This is what we want to find. And in this bottom equation, what I want to find is equal to 2 things minus what I want to find. Well, this means minus one of these, so if I add one of those to both sides, if I say I'm going to add the integral of e to the x sine x dx to both sides, what I'm going to get is 2 times the integral of e to the x sine x dx equals e to the x sine x minus e to the x cos x. So the integral of e to the x sine x dx is going to be that right-hand side divided by 2. And I wouldn't normally, in solving equations like this, show this step, but it's a subtle thing that's happening here. Because, like I said, we end up getting this answer. We end up knowing that the antiderivative of e to the x sine x dx is equal to, there's different ways to write it. I'm going to write it as 1/2 e to the x sine x minus 1/2 e to the x cos x plus a constant. We ended up finding that out without directly anti-differentiating it. And that's maybe the point of many of these techniques of integration. You rewrite the integrand into some other form so you avoid integrating it and you do some other stuff instead.